people can see your screen. So is my screen being shared right now?
Yes.
Okay, so um, can you see my screen
Yep.
in the presentation mode?
Yep.
Okay, just a moment. Do I need to close this or minimize this? Okay. Uh, Good evening, everyone. Thank you so much for taking your valuable time for attending this session today. Thank you so much for giving me this wonderful opportunity. Though it is a last moment for me, I'm really glad to be part of your user group for presenting at your user group. So today I would like to speak on the topic SQL Server internals and architecture. So hopefully you like it. There is a lot of content to grab. So hopefully you like it. So let's get started. A little bit about me. I'm a database administrator with 7 years of experience in managing SQL Server and databases. I'm a Microsoft certified trainer and Microsoft certified solution expert. I did my master's in computer technology at Eastern Illinois University. I blog for dbnuggets.com. That's my website. And you can contact me on Twitter at dbnuggets.com. Sorry, at dbnuggets. That's my user ID. And down below, that's my email address. If you have any questions regarding this session, later, please do not hesitate to contact me. So what are we going to discuss in this session today? We are going to go through the overview of asset properties of transaction with a simple example ensuring the asset properties. And we are also going to go through the different types of components we have in the memory architecture of SQL Server. In this session, we are mainly focusing on the major components of the memory architecture, that's plan cache and buffer pool, and how these cache get managed inside the SQL Server. We are also going to see the life cycle of a query for read as well as a write transaction, like what happens behind the scenes at each component inside the SQL engine. We are also going to see the different types of components we have in the SQL engine, that's relational engine as well as the storage engine. Now, internals, why should we actually care, right? Many DBAs and developers, they work with SQL Server on daily basis, but they might not exactly understand what happens behind the scenes when we submit any query. So knowing this information will help you in understanding how queries are processed at each stage inside the SQL engine. It will also help you in identifying the performance issues very quickly and fix them efficiently. It will also build you confidence while managing the database engine as well as the databases. It will also help you in convincing your coworkers or managers of why they have to take your ideas seriously. Last but not least, we work with SQL Server every day. So the more we know about the internals, the better we can understand how the SQL engine works as well as the database works. Let's start with basic. Uh, let's start with basics. Let's talk about the asset properties of transaction. Now, what is this asset? Every major relational engine, it might be the SQL Server, Oracle, PostgreSQL, Sybase, all these major relational engines should satisfy the asset properties of transactions. So what is this asset? A stands for atomicity. Atomic meaning a single unit of work. A single transaction can contain one operation or it can contain multiple operations in it. All the operations inside the single transaction, whenever it executes, it have to complete successfully or the entire transaction should be rolled back. There cannot be an intermediate state. For example, we have a store procedure, and inside that store procedure, we have two operations in it, the update statement as well as an insert statement. So both of those two statements comes under two operations inside that single transaction. Whenever we execute the store procedure, both of those operations, the update as well as insert, should be successfully completed. If one of them fails, then the SQL Server should roll back the entire transaction. For example, if the update succeeds and if the insert fails, then SQL Server should roll back the entire transaction. That's atomicity. C stands for consistency. The data inside the database should always be consistent before starting the transaction and after completing the transaction. For example, I wanted to do some updates onto a table, and while I am doing that update, something happens suddenly. Like there is a power outage and we have to restart the SQL Server. So once I restart the SQL Server, all these uncommitted transactions should be completely rolled back, making the data in the consistent state. That's consistency. I stands for isolation. So no matter how many concurrent transactions are happening in the SQL Server at the same time, each and every individual transaction should be independent of each other and should not interfere with any other transaction. For example, I am inserting bunch of records into a table. While I am doing that insert, none of the other transactions should be interfering with my transaction. That's isolation. D stands for durability. Once the transaction is successfully completed and all the data has already been made to the database, should be permanent. Like if I had to restart the SQL Server later, then once I restart the SQL Server, all the uncommitted data which is already been made to the database should be permanent. That means there should not be any data loss. That's durability. Now, what components of this SQL engine will ensure this ACID property? Atomicity is very easy to be ensured. It is taken care by the parse component inside the relational engine. Consistency is also very easy to be ensured. It is taken care by the parser and binder components inside the relational engine. If the atomicity, isolation, and durability are ensured, consistency will automatically be ensured. Isolation is all about the locking mechanism. It is taken care by the lock manager inside the storage engine. Durability is the most toughest of all. It is taken care by the transaction log inside our storage engine. Let's see a very simple example ensuring the ACID properties of transaction. For example, here we have, for example, let's take a bank transaction, a very simple bank transaction. For example, I have a balance of $500 in my account, which I have a ID of 1, and I would like to send $100 to my friend's account, which have an ID of 2. So I can do this simple transaction multiple ways, right? I can use the online application, or I can use my mobile phone application, the mobile phone app application of my bank, right? For this example, let's take a mobile phone application. So basically, this simple transaction have two operations in it inside the single transaction. The first operation will be to deduct $100 from my balance, and the second operation is to credit $100 to my friend's account. So once I begin the transaction, once I start the transaction on my mobile phone application, SQL Server will begin the transaction on the background. Once it begins the transaction, it will go ahead and deduct $100 from my account, which is account 1. This is the first operation, which makes up $400. So the second operation is to credit $100 to my friend's account, right? But I suddenly see this on my screen. I see this, I'm logged out of my mobile phone application, and I see this alert saying facility is temporarily unavailable. Now what has happened? I'm in between the transaction. My transaction is not completed yet. I don't know if I lost $100 or if my friend has received $100. So I immediately called her and asked if she received any money, which she said she didn't. So I have no other option except to call the bank customer service guys. So when I called them, they said there was a severe thunderstorm and some of their SQL server went down and they already restarted them. Now just think, if this transaction is ensuring the ACID properties of transaction, what should happen once they restart the SQL server? Let's see what will happen. Once they restart the SQL server, the uncommitted transaction should be completely rolled back, making the data in the consistent state. So this example is ensuring the ACID properties of transaction. Now how? The atomicity is ensured by rolling back the entire transaction. Consistency is ensured by reflecting $500 in my balance, which is the initial amount before starting the transaction. So consistency is also ensured. The isolation part is also ensured. Like, did you observe when SQL Server go ahead and when it deducted $100 from my balance, the first operation inside the transaction, none of the other transactions were interfering with my transaction. So isolation is also ensured. The durability part is also ensured. I do not lose my money. My $100 has been rolled back, and it showed in my balance $500, which is my initial amount before starting the transaction. So once the SQL Server restarted, the transaction log helped make this possible to roll back the entire transaction. So that's how each and every transaction of all these major relational engine should satisfy the ACID properties of transactions. Now let's talk about the SQL Server memory architecture. SQL Server Engine is a Windows program which will use Windows APIs to allocate memory to the SQL Server. Now there are different types of memory architecture inside different types of components inside the memory architecture of SQL Server. In this session, we are mainly focusing on the major components, that's plan cache and the buffer pool. But let's see what other components we have in the memory architecture of SQL Server. The first one, the plan cache, which is one of the major components. It holds the store procedures, query plans, etc. The buffer pool, it holds the 8 KB data pages as well as the index pages in it, which is the buffer pool is the biggest memory component. There are also other types of cache like log cache, token and perm user store cache. Now what this token and perm user store cache does is it will store the user permissions onto the objects. There is also other type of cache known as column store cache, which holds the column store indexes in it. Now basically, all these caches which you are seeing in the blue color are very special. Now, why I say that they are very special? Because they can be easily expanded and shrinked when there is a memory pressure. Now, how can they be expanded easily and shrink? Because they have a backing mechanism in them. Now, what is this backing mechanism? The plan cache, for example, here, the plan cache which holds the store procedures, the query text behind that store procedure is stored inside the system tables. The data pages which are stored inside the buffer pool, those data pages are stored as the database files inside our database disk system, right? The MDF file. And the other caches, the log cache inside which stores the in the other cache, the log cache is stored as the transaction log inside our disk subsystem. The column store cache, which holds the column store indexes, those column store indexes are compressed and those are also stored inside our disk subsystem. Now, all these caches, the major components of the memory architecture, these caches which you are seeing in the blue color, whenever there is a memory pressure, they will be expanded and shrunk easily because they have a backing mechanism in them. Once there is a memory pressure, they will push back all these objects which they are storing and they will be sending them back to their storage system, right? The backing up stores. But what about the fixed memory which you are seeing in the green color? Fixed memory is known as fixed because it cannot be expanded or shrinked when there is a memory pressure. Usually, out of the memory architecture, out of the memory inside our SQL Server, there will be less than 1% of the fixed memory. Now, what will happen if this fixed memory is full? Because it cannot be expanded and shrinked. Now, why it cannot be expanded and shrinked? Because it doesn't have any backing mechanism in them. Like what kind of things are stored in this fixed memory? The connections to the SQL Server, like for example, the connections to the memory grants for the hashes and sorts that we have to the memory grant connection, the memory grants that we allocate to our query even before the query gets executed, right? How much memory that query needs. For example, whenever this fixed memory gets full, then the SQL Server will have an alert system saying that, okay, this fixed memory is completely full. Now I don't know what to do. Then the SQL Server will request these other caches, which you are seeing in the blue color, because these are the major caches and they can be easily expanded and shrinked when there is a memory pressure. So when there is a memory pressure inside the fixed memory, SQL Server will go ahead and request these caches, which you are seeing in the blue color, to release those objects out of those memory and send them to their backing systems. So for example, the plan cache, the store procedures, when there is a memory pressure, these store procedures inside the plan cache will go ahead and they will be pushed out of the plan cache and they will be stored inside the system tables. And that particular cache, which is available right now, will be given to them fixed memory. So that's how the SQL Server will manage this fixed memory. Now there is other type of cache, which is known as SQL Server.exe overhead cache. Now, as you know, the SQL Server is an executable and many things will be running this executable, right? Like for example, the thread stacks. Even this will come under the memory architecture of SQL Server. Now there is different other type of memory known as in-memory OLTP. Now in-memory OLTP also come under the fixed memory. Now this type of memory cannot be expanded or shrinked when there is a memory pressure. There should be some other process which will be kicked in and clean up the objects in it such that there will be the memory which will be available for the newer objects to be saved inside this type of memory. Now, what things will be stored inside this in-memory OLTP? Memory optimized tables are stored inside this memory. Now, this is the overview of memory architecture of SQL Server. Now, let's see how this memory gets managed inside the SQL engine. Now, there is something known as LRUK algorithm, which is known as least recently used algorithm. The hyphen K is for the complexity of the code. Now, what is this LRU? LRU meaning if something is staying in the cache for a longer time, those kind of things will be discarded first. But what happens with the SQL Server? SQL Server will think this way. Like if there is an execution plan, which is created very easily with very less amount of resources and cost, then those kind of execution plans will be discarded first. But what if the execution plan is so complicated? It has been created for the so complicated query that it took so much of resources to generate that execution plan and to be saved that execution plan in the plan cache. Those kind of execution plan will have many chances. Uh, uh, I mean, when compared with the other execution plan, it have more chances to stay in the cache for longer time. Now, how does this memory gets managed? There are two types of processes which will manage this kind of memory. One is lazy writer and the other is ghost cleanup. Now let's see how this memory lazy writer and ghost cleanup works. Now we are taking our example plan cache here. The right side diagram which you are seeing is my plan cache. It's really small. We just have three plans in it, three execution plans in it. Plan 1, plan 2 and plan 3. Now for each and every object we have inside this cache, we have two numbers at the bottom of each object. The left side number is known as complexity code value. The right side number is known as complexity countdown value. Now, lazy writer will be kicked in every minute by the SQL Server automatically. So whenever it is kicked in, what it does is it will go ahead and check if there are any least recently used execution plans. Now, in our example, none of them will be used. So what it does, it will go ahead and see if there are any least recently used execution plan. And if it doesn't find any, for each object, it will go ahead and it will decrement the complexity countdown value by 1 each time it see that it is not being used. So in our example right now, none of them will be used. So it will go ahead and decrement the plan 1 complexity countdown value from 18 to 17, for the plan 2 from 9 to 8, and for the plan 3 from 2 to 1. And the lazy writer will go away. In the very next minute, the lazy writer will kick back in again to see if there are any least recently used execution plans. In our example, none of them will be used again. So it will go ahead and decrement the plan 1 complexity countdown value from 17 to 16, for the plan 2 from 8 to 7, and for the plan 3 from 1 to 0. Now, did you observe the plan 3 complexity countdown value has changed to 0? That means the SQL Server should go ahead and discard that plan out of the cache, right? But that is not what it is going to happen. There is something known as ghost cleanup, which will be kicked in every few minutes by the SQL Server automatically. Now, what it does is it will go ahead and check if there are any execution plans with this no complexity countdown value. Once it finds them, it will go ahead and flag them as ghosted. That means they are still in the memory. That means they are still in the plan cache, but they are in the half life. That means, for example, tomorrow there might be a memory pressure on in the plan cache, right? If there is a memory pressure, then the ghost cleanup will kick in automatically by the SQL Server every few minutes, right? It will go ahead in that particular scenario when there is a memory pressure, it will go ahead and discard these ghosted execution plans out of the cache. But what if there is no memory pressure? SQL Server is still going to keep the other user tomorrow, he might come and use the same execution plan for his query. So that's how the ghost cleanup will work. In the very next moment, the lazy writer will kick back in again to see if there are any least recently used execution plans. Right now, plan 2 will be used. So what it does is it will go ahead and increment that complexity countdown value for the plan 2 to its original value, which is 9. So that's how the lazy writer and ghost cleanup work for the plan cache. Now, before going ahead, if you have any questions, can you ask? Any questions? Adam? So I think there are
I
no.
don't see any questions in the polls
Okay.
for the chat. So unless anybody has something, please speak up.
So it seems like no one have any questions. Can we go ahead?
Looks like Gene has a question.
Sure.
Unmute Gene.
Yeah, that was actually part of it. I was trying to get unmuted, and I seen I was still muted by you. So you can hear me now, right?
Yep.
Yes.
Yeah. So I haven't actually looked at those numbers before. What is a realistic number for that complexity value? Because you had 8, 9, 2. Are
Right.
they usually a lot higher? Because I would have expected the plants to stay in cash longer.
Right. I have researched on that, but I did not find anywhere what is the maximum value. That's a very good question. I had that question before because I know the audience have that question, but I researched for that. I don't know what's the maximum value of that particular complexity code value.
Okay,
But depending upon if it is higher, then that is being used more, right? That is being used more, and once it turns to 0, then the ghost cleaner will come and flag that as ghosted and then remove when there is a memory pressure.
Okay, thanks.
But if I find that, I'm definitely going to I will do more research on that, and I will definitely let you know. Thanks for asking the question. So I'll go ahead and continue now. So let's talk about the buffer pool, like how does the buffer pool gets managed. Buffer pool, basically it holds 8 KB data pages and index pages in it. Basically, it have to manage 3 kinds of different structures in it: the heaps, clustered indexes, and non-clustered indexes. So basically, for example, if you wanted to do a select star from a heap table, you know what will happen. The buffer pool has to go grab all those data pages into the buffer pool and do the operation over there, which is very IO intensive because the buffer pool has to go many trips to grab all those pages. But instead of that, if you put the clustered and non-clustered indexes on the top of it, buffer pool has to will have less amount of IO to go and grab those pages into the buffer pool, and it will basically speed up the query process. Now, how does this buffer pool gets managed? There is something known as a checkpoint process, which will be kicked in every few minutes by the SQL Server automatically. Now, what it does is it will go ahead and check if there are any dirty pages inside our buffer pool. Now, what are these dirty pages? Dirty pages are the pages which are already written to the buffer pool into the buffer pool, but they are not hardened them to the disk. Now, basically, when the checkpoint process kick in every few minutes, it will go ahead and check if there are any dirty pages and push those back and harden them onto the disk. Now, you can also manually run the checkpoint process in your management studio by executing word checkpoint. Whenever you do that, it will just go ahead and grab those dirty pages, push them back to the database file system, and harden them onto the disk. So that's how the buffer pool gets managed by the checkpoint process. Now, this is a very important slide, how SQL Optimizer will choose the plan. As you know, the SQL Optimizer is a cost-based optimizer. It always wanted to choose the good enough plan instead of the best plan. Now, what is the difference? The time and the cost is the difference. For example, if our SQL Optimizer wanted to choose the best plan instead of the good enough plan, what it have to do? For example, we have here a select statement with a 4-table join in it. And each table have a clustered index and 3 non-clustered index on the top of it. Now, in order the optimizer to choose the best plan instead of the good plan, it have to go ahead and analyze 72 different types of physical access method per table. Now, just imagine we just have four join statement here, simple join statement, and 72 per table, meaning we have 4 table join, 72 times 4. Now, these physical access methods, meaning whether the optimizer have to go and do, whether it have to do the clustered index, non-clustered index, or whether it have to do the seek or scan, those kind of physical access methods, per table, it have to analyze 72 of them. On the top of it, it have to go ahead and analyze 24 different types of logical join order just for this simple select statement. Now, what are these logical join orders? We have a 4-table join statement here, right? For example, the join between A to B will filter out 50% of the records from the result set, and the join between B to C will filter out 90% of the records from the result set. Then what the SQL optimizer does is it will go ahead and reorder the join in such a way that it will push the join between B to C front of the statement and push the rest of the joins back of it. Now, why it do that? It wanted to grab the results as soon as possible. On the top of it, it have to go ahead and analyze so many transformation rules, at least some thousands of transformation rules, and it will gather approximately 26,000 possible plans just for this simple select statement. Now just imagine how much time and cost and resources consuming it is for the optimizer to choose the best plan out of these 26,000 possible plans. Now, no user wanted to wait for such long time to get his results, right? That's the reason the SQL optimizer will go ahead and grab the good enough execution plan by analyzing only few optimization rules as quickly as possible. Once it find out the good enough plan, it won't go ahead. It will just grab that good enough plan and it will save that execution plan in the plan cache. Now that's the reason why the optimizer is so quick. And I would like to thank Kevin Klein for loaning me this example. If I explain the same concept in a simple words, for example, if the optimizer choose the plan A, execution plan A in 3 milliseconds and execution plan B in 3.5 milliseconds, and in order to analyze if the plan A is better or B is better, if it has to go and analyze for 5 minutes, the optimizer doesn't want to do that. It will just go ahead and grab plan A or plan B randomly. That's how the optimizer works. And now let's talk about the life cycle of a query. If the life cycle of a query is divided into 3 different steps, the first step contains the components parser, binder, simplification, and the trivial plan. Now these components from the first step are very lightweight and very easy to the SQL server. Now it doesn't need much metadata at all except for the table and the query definitions. That's all it needs. When you come to the second step contains the components load metadata, join heuristics, and search phases. Now, all these components from the second step, they require the most of the metadata that it requires to process any of the query. Now, when you come to the third step contains the components access method, transaction manager, and buffer manager. Now, when you compare with the first step and the second step, the third step components are very IO intensive. Now, why I say that? Because we have a buffer manager component in it, and it have to go ahead and grab the database pages and the buffer pages into the buffer manager, right? That's the reason why it is very IO intensive. Now, the first step components and the second step components will come under the relational engine, and the third step components will come under the storage engine. Now let's see how the select query works behind the scenes. What happens behind the scenes at each component when we submit a select query. For example, we have a user here. No matter what kind of interface he uses, he might be using the SQL Server Management Studio, Azure Data Studio, .NET Visual Studio, or even a third-party application. No matter what kind of interface he uses, once he submits the select query to the SQL Server, he should first get the secure network connection to the SQL Server. Now, how does he get that? There is something known as SQL Server Network Interface, which is also known as SNI. Now, what this SNI does is it will establish a secure network connection to the SQL Server as well as the client. Now, the client is our user here. Now, how does it secure? It connects the secure network connection by using the internet protocol. There are several types of internet protocol like TCP, IP, named pipe, shared memory. No matter what kind of internet protocol we use, the process remains the same. Now, once the secure network connection has been established between the SQL Server and the user, the query that the user is sending is wrapped inside a tabular data stream packet, which is also known as a TDS packet, and SNI will wrap this into the TDS packet, and it will give that TDS packet to the SQL operating system. Once the TDS packet has reached to the SQL operating system, the SQL operating system will identify that coming connection as a SQL connection, and it will assign a SPID to it. You know the SPID, right? The SQL process ID. Whenever you run the SP-who2 or SP-who, you will find the SPID number 6794. Those SPIDs are the active connections which are made to the SQL server. So once the SPID is assigned by the SQL operating system, the tabular data stream packet will be unwrapped, and then that coming query is identified as a SQL query, and it is given to the first step inside our relational engine, which is the parser. So the parser is the first component inside our relational engine. Now what this parser does is it will just validate the syntax of it. For example, if you wanted to do the select star from a table, but by mistake you have given select star from, at this component, the parser component, parser should identify that as a syntactical error and throw back the error to the user. And at this parser component, the variables are also declared. For example, if you are not declaring the variables properly, parser will identify that as a syntactical error too. And views are expanded here. If at all you are using a view inside your select statement, then the code text behind that view will be brought in line into the code we are sending. That happens at the parser component. Now with all this information, what the parser does is it will put a hash on our query that we are sending, and it will go ahead and compare the execution plan inside our plan cache. If it finds the exact match of the execution plan for that query, then it will go ahead and use the same execution plan for the execution phase. But what if it doesn't find the same execution plan? It will go ahead and build the initial logical tree at the parser component. Once it builds the initial logical tree, our query will be sent to the binder component. Now the binder is also known as algebraizer or the normalizer. Now what happens at this binder component is binder will identify and validate the objects of the objects that we are using in our query, right? Whether they are valid or not. The parser is the one which will just identify the syntax, but the parser will just identify the syntax, but the binder is the one which will validate the objects as well as the tables, whether they are valid or not. And checking the user permissions happens here, like the user, whether he have the enough permissions to execute those objects, to run those objects, those kind of user permissions are checked here. And data type resolution also happens here. Now, for example, if you wanted to do a select in between the two tables and you are using a union all clause in between those two tables, the ordinal column of those two tables should be matched in the data type. Those kind of things are checked here. I will show you in our demo like what I mean by data type resolution and how it works. But for now, just remember that the data type resolution, like the data type should match. And the aggregate binding happens here, like the sum, average, those kind of things are bound here. With all this information, the parse tree inside our plan cache is once again updated, and then our query is now sent to the simplification component. Now what happens at this simplification component is, by name itself, we know that it can simplification. By the name itself, we can say that it simplifies the query, right? Now, for example, if you are sending a select query which have a subquery in it, now behind the scenes, whenever you run a subquery onto the SQL server, behind the scenes, the simplification component will go ahead and convert that subquery into a simple join. Now this happens all the time behind the scenes. Now contradiction detection also happens here. For example, if we have a foreign key contradiction, those kind of things are checked here. With all this information, the parse tree is once again updated inside our plan cache, and our query is now sent to the trivial plan component. Now what happens at this trivial plan component? For example, we are sending a very simple query, select star from a table or select star from a table with a simple where clause. Then what SQL server thinks is, this is such an easy query. This is such a simple query. Why should I even go ahead and update the parse tree inside the plan cache that these previous components has built? I will just go ahead and discard that parse tree inside the plan cache, and then I will just on the fly create a trivial plan, because it doesn't cost me much. It doesn't cost any resources or cost to create a trivial plan. No matter how many times the user is running that query, he might be running 10,000 times. I am going to create the trivial plan 10,000 times because it doesn't cost me much at all. And SQL Server, it doesn't store the trivial plans inside the plan cache by default. Now there are options to store them, like to convert these trivial plans into full plans and store them inside our plan cache. But SQL Server doesn't want to store them inside the plan cache because you don't want to waste the memory inside the plan cache for these simple queries, because it doesn't cost it much to create on the fly. Instead, it wanted to save that memory inside the plan cache for more complicated execution plans. Now, what if our query is not so simple? What if our query is so complicated with so much of logic uh, inside it? Like, what if we are using 10 tables with a um, group bys, order bys, and complicated logic in it? Then SQL Server will identify that as a complicated query, and it will be sending that query for the second step inside our relational engine to create the full plan. So once our query has reached to the second step inside our relational engine, the first component inside our second step is load metadata. Now most of the metadata that it requires to process any query are gathered here. For example, the index statistics and histograms. Now index statistics are the blob structures that are created by the SQL Server. Now what they do is they describe the distribution of the data inside a column or set of columns or an indexed view of a table of a column basically. So those kind of index statistics are gathered here, and auto create statistics happens here. If your auto create statistics option is turned on or in your database properties, then for example, if you are sending a select statement very frequently and searching on a column very frequently, and that column doesn't have a statistics on it, and if your auto create statistics turned on the database properties, then SQL Server will go ahead and create statistics on that particular column, even though if that column doesn't have any index on it. So cardinality estimates are also gathered here. Cardinality estimates meaning how many number of rows that the optimizer thinks that it is going to come back out of a table, or how many rows that it will come out of each operator inside our query tree. Those are called the cardinality estimates, and these cardinality estimates are really important um, for a good enough plan to be generated and stored inside our plan cache. Now when they go wrong, the non-optimal plans are generated and stored inside our plan cache, which will eventually cause the performance issues of the query. And SQL Server and Windows collations are also checked here, and set options are also checked here. For example, the set XML on or set XML off, set ANSI padding on or off. Depending upon on or off, the execution plan might be dependent. And with all this information, the parse tree inside the plan cache is once again updated, and then our query is now sent to the join heuristic phase. Now, what happens in this join heuristic phase is, I discussed this reordering of join in the previous slides, but let me re-explain again. Now, if we have a very simple select statement with three table joins in it, and the join between A to B will filter out 60% of the records from the result set, and the join between B to C might filter out 99% of the records from the result set. Then the optimizer will go ahead and reorder the join in such a way that it will push back the join between B to C, front of the statement, and A to B join, back of it. Now, why it do that is to get the results as quickly as possible. Now, with this information, the parse tree is once again updated inside our plan cache, and then our query is now sent to the search phases. Now, what are these search phases? In the very next slide, we are going to discuss what are these search phases are and how the optimizer will work on them. But just remember now that our SQL optimizer is a cost-based optimizer. It always wanted to choose a good enough plan instead of the best plan. So how does it choose the execution plans is, it will go ahead and grab the good enough execution plan from these three phases, the phase 0, phase 1, and phase 2. Once it finds the good enough execution plan, it will go ahead and update that thing inside the plan cache, and it will finally put a hash on that execution plan, and it will send our query to the storage engine component. Now, the third step of storage engine, right? Before going into the storage engine, let's see what these search phases are. So basically, the optimizer, no matter what kind of query we are sending to the SQL server, the optimizer has to go and grab the execution plans from these three phases. The phase 0, which is also known as a transactional plan. All the execution plans here are created at the pre-optimization stage. Now, what is this pre-optimization stage? All the components that we have discussed in the phase 1, the step 1, that is the parser, binder, simplification, and the trivial plan, those components will come under the pre-optimization stage. Now, if all the trivial plans are generated at this phase 0, right? The trivial plan component is in the first step of relational engine, right? So the trivial plans are generated there. Now, these plans are created very quickly, as soon as possible, with less amount of basic heuristics are needed, like mostly the query definition and the table definition, with less amount of heuristics that are needed to create these plans. And these plans are created for very small queries, like with maximum of 3 tables in it. That's the phase 0. Now, when you come to the phase 1 execution plans, these plans are also known as quick plans. Now, these execution plans are created for the queries with maximum of 8 tables in it, and more transformation rules are needed than the phase 0. Now, what happens with the phase 0 and phase 1 is, the optimizer will take the query which we are sending, and it will go ahead and compare with already existing execution shapes. Once it finds a good enough execution plan out of those shapes, it will go ahead and grab the execution plan from these two phases. But that is not the case with the phase 2. Phase 2 is known as full plan. Now, the full plans are created here, and these plans are more complicated. These plans are created for more complicated queries, like most of the parallelism, spills, and spools to the TempDB happen here. Most of the transformation rules are unlocked here. Now, what the optimizer does is, it doesn't compare our query with the already existing execution shapes in the phase 2. But instead, what it does is, the optimizer will go ahead and prune off all the transformation rules that we are not using. Now, what I mean by that is, for example, we are not using nvar max or blob data types in our query that we are sending to the SQL server. Then optimizer will first go ahead and prune off all those rules which we are not using. And then it will go ahead and analyze some of the optimization rules as quickly as possible, so that it can grab the good enough execution plan. So that's how the phase 2 execution plans are generated. Now our query is at the storage engine component, right? First, let's see the read transaction. For the read transaction, what happens? Now, before going into these components, no matter what kind of query we are sending to the SQL server, it might be the read transaction or write transaction, it have to pass through the first step and the second step of the relational engine. If our query is so simple that the SQL server go ahead and it created a trivial plan, then it will grab the trivial plan and go to the execution phase and come to the storage engine component. But what if our query is complicated? Then it have to pass through the second step of the relational engine and then to the third step of the storage engine. But all the difference happens here at the storage engine is at the transaction manager component and the buffer manager component. Now let's see what the differences are for the read and the write transaction. Let's discuss about the read transaction first. The first component inside the storage engine is access method. Now the access method by itself, it doesn't do any operation by itself, but what it do is, it will analyze how it have to gather the results from this subsystem. That's all it does. When the query is sent to the transaction manager component, there are two subcomponents inside this transaction manager, the log manager and the log manager. Now this is a read transaction, right? So what the transaction manager does is it will go ahead and invoke the log component of it, the log manager. It doesn't invoke the log manager. Now you know why. Because we are not, for the read transaction, we are not modifying any data pages inside the buffer pool. And we are not doing any modifications, right, to the tables. So that's the reason transaction manager doesn't invoke the log manager part of it, but it will invoke the log manager part of it, and it will request the buffer manager to put a shared log on the resources that the buffer manager needs. Now, why shared log? Is because it is a read transaction and we are not making any modifications to the tables. So we doesn't need any exclusive log. So once the query is sent to the buffer manager component, buffer manager, it will first put the shared lock on the resources it needs. It will go ahead and then check if all the resources that it needs for satisfying the query are already in the buffer pool. If it doesn't find some of them, or if it doesn't find any, it will just go ahead and grab those pages in the form of 8 KB pages, put them in the buffer pool, do the operation over there, and send the results to the user. Read transaction, very simple. But what happens with the write transaction? As I told you, the difference is at the transaction manager and the buffer manager. Access method by itself, it doesn't do any operation. It will just analyze how it have to gather the results from this subsystem. Once this query has sent to the transaction manager, now the difference is here. Since it is a write transaction, the transaction log will be invoked first, and all the modifications that the transaction, all the modifications that we are trying to make inside our data pages in the buffer pool, before writing anything into the buffer pool, first those changes are written to the transaction log. Now, why it does that? Because if something happens in between the transaction, there is a transaction log be there to revert back the entire transaction, roll back the entire transaction that we discussed in our asset properties of transaction, right? And once it has returned to the transaction log will invoke the log part of it and the log manager part of it, and it will request the buffer manager to put an exclusive log on the resources that the buffer manager needs. So now, why exclusive log? This is a write transaction and we do not want any other transaction to be interfering with my transaction, right? The asset properties again. So once the query has reached to the buffer manager component, now the buffer manager component will put an exclusive log on the resources it needs, and then it will go ahead and check if those resources are already in the buffer pool. If it didn't find some of them or all of them, it will just go ahead and grab those pages back into the buffer pool in the form of 8 KB pages, just like the read transaction, and send the success message to the user. Now, did you observe the data pages has already been modified in the buffer pool, but they are not hardened them onto the database file system, right? Now that's when the checkpoint process will kick in. It will go ahead and check all these dirty pages inside the buffer pool. It will go ahead and push those and harden them onto the database file system. Now that's how the write transaction works. Now let's see the demo of how these pre-optimization phase works, like how the parser, binder, simplification, and the trivial plan components works behind the scenes inside our management studio. Now let me hop back into my management studio. Can you please confirm that you are seeing Adam management studio?
Yep.
Awesome. So for my demo, I'm using AdventureWorks 2016 database. And then first I would like to show you how the parser works. So we can parse in two different ways. We can set the parse only option on, or you can use the parser option here inside our management studio. But let me set the parse only option on. This will just invoke the parse component of it. Now I'm going to execute that. Now it's turned on. Now I wanted to do a very simple select statement which do not have any syntactical errors. So when I execute this, it should not, the parser will not execute the results, or it doesn't generate any execution plan. All it does is just validate the syntax. Now variables are also declared at this parser phase, right? So I did not declare the variable, but I'm simply using the variable in the where clause. Now when I execute this, it should throw me an error saying must declare the scalar variable. Now I want to do a select on non-existing column, select non-existing column from a non-existing table. Now when I execute this, it doesn't throw me an error because this is the parser. Parser doesn't identify and validate the objects. It will just identify the syntax, right? So that's the reason it won't generate any error. So let me turn off this parse only option off, and let me turn on the format only option on. So when I turn on this parse only format only option on, it will invoke both the parser as well as the binder components of this pre-optimization stage. Let me turn on that. And then let me do a very simple, let me check like whether all these objects inside this particular select query are valid or not. Now everything is valid, so it doesn't throw me any error. And also even the format only option, it doesn't generate the results, or it doesn't generate the execution plan. It will just validate the, it will just invoke the parser and binder components of it. Now this time let me execute the select non-existing column from non-existing table. Now when I execute this, this should throw me an error because binder component has kicked in, right? Now let me turn off the format only option off. And let's see how the data type resolution works. Like I discussed, right? Whenever you have a select statement inside the tables, the ordinal columns of those two tables should be of the same data type. Now the customer ID, if you see here, it's an integer data type, and sales order ID is also of an integer data type. Now when you execute that, it doesn't throw me an error, right? But what if I go ahead and manually create the data type resolution error? The customer ID here is of an integer data type, and the credit card approval code here is of varchar data type. Now when I execute this, it should throw me a conversion fail error. Now that's how the parser and the binder works. Now let's see how the simplification and the trivial plan works. Now let me put this in on the database context. And I wanted to show you like how the subqueries are converted into the simple joins. Now this is a very simple subquery. Let me turn on the actual execution plan on. And when I execute this, when you go to the execution plan, now did you see here, it just converted into a simple inner join. Now that's how on the background, whenever you submit a subquery, SQL Server will go ahead and convert that into a simple join. Now here, let's see if the simplification also will remove the redundant joins. For example, here we have a select statement between two tables, but here, if you observe, we are all getting the columns from just the sales order header table. We are not touching the customer table at all. So when you execute this, we are simply using the customer table just like that here. We are not getting any columns out of it. Now, when I execute that particular query, when you go to the execution plan, SQL Server will not even touch the customer table because that's a redundant join. We are not using that table at all. So it will go ahead and grab all the results from the sales order table, sales order header table only. And then now let's see contradiction errors, right? I manually created the contradiction saying where territory ID is equal to 1 and where territory ID is not equal to 1. Now when I execute that, it should not throw me any results. It should not throw me any errors, but it will also not show me any results, right? Now why it did not create any error? Because SQL Server, this is a pre-optimization stage, and SQL Optimizer doesn't know what value we are using in this where clause, like for these variables, right? If we might be using 1,000 or we might be using 10,000, it doesn't know. So that's the reason we did not have any error. Now, this is a very simple query here. Let's see if the trivial plan gets generated. It is a very simple query with select statement with a very simple where clause. Now, when I execute this and go to the execution plan, do the properties on the select, and when you check here, the optimization level is of trivial. So because of the SQL Server has thought this is a very simple query, no matter if the user runs this 10,000 times, the SQL Server is going to create the trivial plans 10,000 times, and it is not going to save these trivial plans inside our plan cache. By default, those are not saved. But what if some cases, even though we don't want the SQL Server to create it as trivial plan, it will go ahead and create the trivial plan. And what if you want to save the trivial plan into a full plan? What if you want to force that to convert into a trivial plan and save that plan inside your plan cache? There is an option for that. Now, I do not recommend that to do it in the production. There are always some cases where you want to do that, but there is a reason why the SQL Server doesn't save these plans inside the plan cache, because it always wanted to save that memory for the more complicated execution plans, right? But there is an option when you turn on the query, the trace flag 8757. When you turn on the trace flag for that particular query, it will go ahead and convert that trivial plan into the full plan and save that plan inside the plan cache. Whenever you turn on the trace flag option 8757 on for that particular query, it is just for that particular query. It doesn't cause any effect to the database itself or the server level. It is just bound to that particular query. Now, when I execute that query and then go to the execution plan, do a select, go to the properties, and when you see the optimization level, now this particular query has now generated a full plan, and now it's been stored inside the plan cache. Now that's how the simplification and trivial plan components work. Now let me quickly hop back into my slide back again. So in this particular session, we have actually gone through the overview of ACID properties of transaction and how each and every single transaction of all the relational databases should satisfy. And we have seen with an example ensuring the ACID properties of transaction. We have also gone through the overview of different types of components we have in the memory architecture of SQL Server. In this session, we have mainly gone through the plan cache and buffer pool and how they get managed. And we have also seen the life cycle of a query for the read as well as the write transaction, like what happens behind the scenes at each component inside the relational engine. And we have also gone through the different types of components and steps we have inside our SQL engine, the components, the relational engine, as well as the storage engine. Now, to prepare for this presentation, I have gone through many resources, and mainly I have gone through these resources. Kevin Klein have wonderful resources about internals. If you wanted to know more in deep into the SQL Server internals and architecture, please go ahead and you can view his articles and webinars. And I would like to thank Adam one more time for giving me this wonderful opportunity to speak for your user group. And in the next month, I'm going to present on the topic SQL, diving deep into the statistics of SQL Server, like what happens if they go wrong, how to view them, how does they affect the performance of the SQL Server, and why it is so important to update them, and what are the ways we can update them. So I would like to thank you one more time. And if you have any questions, please ask me now. Adam.
Hey there, guys. If you do have a question, feel free to raise your hand or put something in the chat. There's anything out there? We normally do have a kind of quiet group, so it's not a surprise.
Mm-hmm. And well, I can also share you the, yeah, go ahead.
Oh, I was going to say, I'll be posting, I'm recording the session for tonight, and I'll be posting that up on our website. And then if you can send me your slide deck, I can get that put up there as well. And with any of the scripts or anything as well, I can get those attached as well, so people can review those and check them out too. So if there's nothing else, guys, I'll probably end up closing out and meeting next month. It'll be the same as usual. So it'll be on December 8th. And I'm not sure, I'm still working out times and everything. I don't know if we'll have to do it at this time again, or if we'll go back to the 5:30, but whatever works with Deepthi's schedule. So I'll make sure to get that out there so everybody can see that for next month. So
Sure. So I have shared my GitHub repository for the slide. We have slide and demos inside it. So,
great.
Yeah. Thank you so much, Adam, for giving me the opportunity.
Yeah, it was great meeting you, and you did a great job.
Thank you.
All right, guys. I will see you guys next month. Have a good night.
Have a good night, everyone. Thank you so much for attending again. Bye.